We'll now go to the second presentation, and that presentation will be made by Tasos Papathanasiou from Langan Engineering. Tasos, the floor is yours.
Good afternoon, or again, good morning, or thank you for the opportunity to present our findings from projects that we have performed, and discussing about the value of testing in these projects. Today's presentation, I will discuss the installation and testing of piles in two projects in New York and Brooklyn. And before starting, I would like first to thank my colleagues who helped me. No project is happening by itself. There's tremendous effort and a team responsible for these good results. So Kostis Ingros and Vijay from Langan, and also I want to thank the contractor who installed the piles on both projects, and the rebar manufacturer who actually provided valuable input during the design and the installation process. So so today I'm going to give some insight on the design, installation, and testing of different piles types in two sites in Brooklyn. The two sites have substantially different geologic settings, and what was extremely interesting for us was that both foundations, both the piles were installed by the same contractor, actually using the same operator and the same equipment. So we had the opportunity to just normalize for means and methods and focus on soil values and pile types, and get as much as possible the human factor out from this exercise. We cannot stress enough the value of testing on both projects. We had long discussions with the clients in order to convince them to spend the extra money, but at the end of the day, when they realized the savings in terms of cost and schedule, they were on board and grateful for going in that direction. So a quick overview. We're going to present the sites and the geologic settings, our subsurface investigation, then spend a little bit of time discussing analysis and design, the types of piles, the index piles, and the testing program. We're going to discuss the field testing and what we found, and then we're going to finish with our conclusions. So physical setting, we are in New York City, and specifically we are in Brooklyn. The two sites, 86 Fleet is on the north side of Brooklyn, downtown Brooklyn, and the other side is less than 10 miles to the south in coastal Brooklyn. The name of the site is 1501 Voorhees Avenue. So geologic setting, which is very important, proved to be very important for the design process and the selection of the piles. As many of you know, the last glacial advance came as far as New York City. The Wisconsin ice sheet left marks in the city, depositing rock and soil debris, and is responsible for the hilly areas that are running through the 5 boroughs. So according to geologists, the Wisconsin ice sheet began moving southward from Labrador about 90,000 years ago, and it stopped right at the middle of Brooklyn, where in our slide says Terminal Moraine. This was the limit of the ice sheet, which basically means that during the ice melting, all the boulders and cobbles that were carried with the ice sheet just basically landed in that area of Brooklyn, and are found during investigations and foundation excavations. Boulders and cobbles and boulders actually sometimes the size of a car. On the north side, there is a ground moraine, it's more lake-like deposits, while on the south, just south of the terminal moraine, we have the outpost deposits. When the glacier was melting, the finer parts were melting and carried by the water towards the ocean. So I'm going to continue with the presentation with presenting side by side the two sites. So 86 Fleet, again, downtown Brooklyn, about 33,000 square foot of footprint, lot line construction, relatively high on elevation 31 to 39. There was an adjacent 40-story tower and a New York City Transit tunnel about 130 feet away to the west of the site. In New York City, whenever a project is happening within 200 feet of New York City transit structures, tunnels, or stations, the investigations and the foundation design needs to be reviewed and approved by transit. And column loads in this project were up to 2,700 kips. On the other hand, in Voorhees Avenue, the project, the site, the footprint actually of the building was about half the size in a much larger site, lower elevations, which actually put us in the floodplain. And all the surrounding buildings were low rises, nothing in the area, as you will see in the next couple of slides, were not more than 4 to 7 stories. And again, there is a New York City Transit embankment this way, not a tunnel, immediately to the west of the site. Column loads for this project a bit lower, 2,000 kips. So 86 Fleet ended up being a 42-story building, and the project in Voorhees Avenue was about 30 stories. Next slide is 86 Fleet before construction happened, so you get an idea of the actual setting. To the west is the existing tower, lot line construction, and further to the west, of course you cannot see that, is the entrance to the subway tunnel. This is the location, the future location of Voorhees Avenue project. It's an engineering rendering. Engineers are not as good as architects putting renderings together, but basically this is with this slide I want to show the size of the building compared to the surrounding buildings. You get the idea that it's the highest building in the area, up to 30 stories. And at that point, there were not any data around regarding foundation construction for buildings of this height in this area. So we felt that we were just in terra incognita or breaking new ground over there, and it was an opportunity to test and discover something new in this area of Brooklyn. So the subsurface investigation programs, the number of borings in New York City is defined by the building code, and the number of borings depends if the engineer anticipates shallow or deep foundations. So for 86 Fleet, we performed 15 SPT test borings. We went as deep as 122 feet. The rock is about 100 to 110 feet deep, so we end up coring some rock. We installed also monitoring wells, and we performed test pits along the property line with a neighbor to investigate what kind of foundations they were on. On the other hand, we had more borings available and more subsurface investigations for 51 for the Voorhees Avenue project because the the site has changed hands many times, and the different owners wanted the building at different spots at this big site. So several other consultants performed borings before us, and we use all this data, and actually we perform some additional borings of our own just to fill the gaps. So at the end of the day, 36 SPT borings were available to us, with depths from 50 to 100 feet deep, some monitoring wells, a few test pits to investigate the presence of former foundations at the site. Some old maps were showing some old structures. And we also performed some 4 CPTs to 100 feet deep. We did not perform CPTs in Myrtle Avenue, in the 86 Fleet, because of the presence of the boulders and the density of the soils, it's not really feasible to push SPTs in downtown Brooklyn. A summary of the subsurface conditions, again, on the left side, 86 Fleet, big picture, fill over sand, medium to dense sand, boulders and cobbles 30 feet down, and then rock was, again, 90 to 100 feet deep. On the other hand, in Voorhees Avenue, it was fill, overland sand, to great depths. In this area of Brooklyn, bedrock is more than 500 feet deep. So the big difference between the two sites, the density of the sands, SPT values on 80 feet place were like from 20 to 80 blows per foot, around 30 at the foundation level. And then on the other hand, the upper sand at Voorhees Avenue was from loose to medium dense, and density increased with depth to about 50 blows per foot. So these are the subsurface findings in terms of SPT N values with depth. Again, you can see that the lower N values or SPT values from Voorhees Avenue compared to 86 Fleet, and the bump in the SPT values at about 30 feet deep, where we encountered this very typical zone of boulders and cobbles in downtown Brooklyn, where at this the location of the terminal moraine. And on the right hand side, the CPT results. So this is a fairly loaded slide in terms of the it not presents the extent of the effort coordinating with the structural engineer and the architect in order to come up with the initial design for the project. So we had very strict total and differential criteria on both projects. We dealt with the sensitivity of nearby structures and mostly the sensitivity of the transit authority structures. And of course, we had to consider economy in the design. The soils on the 86 Fleet site had adequate bearing capacity to support the mat, but we had problems with differential settlements, heavily loaded columns, and the core. So we didn't have any bearing capacity issues, but we had to deal with differential settlements. On Voorhees, we had a different condition. The upper sand was very loose. Supporting the building on a mat was not really an option, was going to result in really large settlements. And the project, after evaluating several options, we end up considering a mat on drilled piles. And drilled piles were selected because we were sensitive and the owner was sensitive to the neighborhood. Again, if you remember from the previous slides, this is the tallest building in the neighborhood. There was no experience in the neighborhood with this type of construction and pile driving could not could have been what the client was saying, a public relations disaster at that point of the project. So we started by considering that the entire foundation was going to be on drilled piles. That was the initial design. We discussed with ownership on both projects to go out and basically get pricing from contractors for the projects and basically evaluate with them value engineering options and consider testing in order to make the foundation design more efficient and kind of what the owners want to say, sharpen our pencil. These projects happen with clients that we have relationships for a long time. This is also very important. Trust is very important when the consultant is asking for additional testing and beyond the code requirements. It has to be explained well, but I have found that trust and long-term relationships are also important in order to convey the message appropriately. So after discussing with the specialty contractors and the specific specialty contractor was on board, we ended up with putting a testing schedule together for the following elements. For 86 fleet, since we're not supporting the project on piles, but it was going to be a mat foundation with localized supports, additional supports, in order to limit differential settlements. These are ground improvement elements, are not typical conventional piles. These elements were designed to be initially to be 50 feet long, 10-inch diameter. And again, these are not piles. The goal was to test them to failure in order to get the ultimate side shear. And these elements are working together with the mat foundation. The mat needs to settle together with the GIEs in order for these elements not to be hard points. So we estimated using conventional methods about an ultimate capacity of 190 tons for these elements. Now, for Voorhees Avenue, we considered conventional micropiles, 100 feet long. The bond length was 80 feet. The estimated allowable capacity was 150 tons. Then we also considered hollow bar micropiles. I'm going to take a little bit more in a couple of minutes about what's the difference between these pile types. Again, total length 100 feet, about similar diameter, and the estimate capacity was 180 tons. And then we spoke with the client in order to spend the money and make an effort to see if we use driven piles at Voorhees Avenue, what would be the measured vibrations around the neighborhood, what would be the reaction of the neighborhood to the driving, and the comparison between the costs of mostly driving to mostly drilling was so substantial that a rig mobilization and installation and testing of driven index piles was justified in order to reduce the cost of the project. So we agreed with the contractor that we were going to try taper piles, 100 feet deep, with a taper of 25 foot long taper, and we used several conventional methods to estimate the capacities. We got between 165 tons to 280 tons, depending on the correlations that we used. So moving in the index pile installation and testing. So for 86 fleet, we installed and tested 2 instrumented ground improvement elements. Again, we call them ground improvement elements because they're not acting as piles. The goal was to fail them during the design. Strain gauges were used to instrument the piles, and we generally followed the procedures of the New York City Building Code for the testing, which basically ASTM standards with 12 to 24-hour hold and cycling testing and cycling loading. For the Voorhees Avenue project, the index pile installation consisted of 2 conventional micropiles, 2 hollow bar micropiles, and then 6 driven piles. The driven piles we performed PDA and high strain density testing. And in the end, based on the PDA results and the installation that was observed in the field, we performed 1 test on conventional micropiles, 1 on hollow bars, and 2 load tests on driven taper piles. Now, one thing that should be noted is that the building code requires testing to be performed for when buildings are supported on piles regardless. So for Voorhees Avenue, the code we require to do 2 tests. So basically from the owner, we convinced them to perform 2 additional tests. For 86 Fleet, it was more of an uphill battle because the foundation was a mat foundation. We didn't really need to perform any testing, but we convinced them that the design of the ground improvement elements could not proceed successfully just by desk studies, and we needed real field test results in order to fine-tune the length of these elements and make sure that they worked together with a mat foundation and they don't act like stiff elements that would actually crack the mat foundation. Again, I want to stress out, I think at least I was excited as an engineer to have the same contractor and driller and equipment on both projects when it comes to the drilling of the piles. This is a rare opportunity to normalize my results for the means and methods of the contractor and compare geologies and different types of piles for what they are and what the driller and the contractor is capable of doing. Just want to spend a few minutes discussing the elements themselves. So the GIE is essentially a micropile, almost 10-inch diameter micropile with a predicted ultimate capacity of 190 tons. Nothing magic about it. 1 bar at the center of the pile and 6 KSI pressure grouted element. The installation was performed using duplex drilling and internal flush, installing the casing all the way down to the bottom of the pile. Now, the experience of the contractor in the area was that the hole could not stay open just with drilling with water. So his recommendation, which we adopted, was to use a polymer mud. However, we were skeptical regarding the effects of the polymer mud to the side friction of the piles, and this is why we selected, as we'll see later, what we think now was a rather longer length of GIE that we should have considered in the beginning. We didn't know exactly what was going to be the effect of the polymer mud on the side friction. So the rest of the installation is typical. The casing is stuck to the bottom of the pile. then the rebar and the tremie grouting follows, and then the casing is withdrawn all the way up. The production for this site was 2 piles per shift. Some information regarding the instrumentation, telltale rods, top, middle, and toe of the piles, vibrating wire rebar, and the strains were recorded with a digital readout. Moving now to the Voorhees Avenue project. Conventional micropile, very similar, but now we are talking about a larger diameter. We jump from almost 10 inches to 13.4. One rebar at the center of the pile, much greater bond length in order to get the required capacities. Again, the sands over here were much looser, and again 6 KSI grout. The installation followed the same process. Again, the driller was adamant that we should use polymer fluid and not just water. I mean, the sands over here much looser. We were more in agreement for this side. We're skeptical for 86 fleet, but over here made more sense. Same process again, but for this project, because the piles were much deeper, the contractor was able to get 1 pile per shift. And this is the hollow bar micropile. Basically, this type of pile, the drilling rod and the drilling bit are sacrificial. The drill rod is advanced all the way down to the bottom of the pile tip. Grouting is performed at the same time with the drilling. Again, the bit is sacrificial, and with this system, this system is very contractor friendly. Basically, there are no extra steps with taking the casing down, then cleaning the pile, then tremie, grouting, and put the reinforcement. It's one step. The reinforcement is the drilling string, and then the grouting is happening as the contractor is drilling. So the problem or the challenge with this type of pile is that the New York City building codes and other codes limit the structural capacity of this pile by not allowing to consider the grout that is outside the reinforcement, contributing to the structural capacity of the pile. So you can get really high geotechnical capacities with this pile, but then it's the structural capacity is limited, and the understanding and the discussion we had with the client was that if we have found that the testing and the testing results were super favorable, and the cost of this pile was also very attractive, we were going to apply to the building department for a waiver, presenting the findings of our results and presenting a report in order to get relief from and they allow us to use the contribution of the grout as part of the structural capacity and have a larger overall capacity for the pile. So we spoke about the installation of the hollow bar. We covered all this, and again, I should say that the drilling started with using polymer fluid, and then the contractor at one point switches to grout and grouts the pile, moving from top to bottom, and the production rate was 1 pile per shift. Again, these piles were about 100 feet deep. And lastly is the driven elements, are the taper piles, 100 feet long with a taper section of 25 feet. The contractor proposed a 5/8 Jonathan hammer. We thought that it was a light hammer for this application, correct? Considering the depth of installation. As you will see in the next slide, it took significant effort to advance the piles to the required depth. In retrospect, we could have used a 7 or a 9. However, the contractor was very skeptical regarding the driving stresses and destroying the pile at the top. So, and they took upon them the additional time for driving the piles. Preliminary PDA results in the field. So the predicted ultimate capacity for the 3 piles were between 215 to 240 tons for a significant number of blows, 140 over 8 inches to about 300 blows for 12 inches. Again, we discussed with the contractor that this is a significant effort that can delay the project, but again, basically it was a risk that they were willing to take. Important topic to discuss is that with this type of piles and for this area and these soil conditions, the testing had to be performed 3 to 4 weeks after driving in order for the soil to freeze around the piles. As we see, the PDA results just before the testing for the strike were significantly higher than the original PDA results. So something we expected it, but we want to see how much the predicted capacity of the pile will decrease with 3 to 4 weeks a waiting period. And we move to the field testing results. So these are the 2 piles for 86 fleet. The lines show the building code criteria. It's basically the failures as defined by code is elastic shortening plus 3/4 of an inch. The dotted line shows that although we tried then to cyclic the test, we were not able to reach failure. We wanted to keep loading, but the contractor's engineer recommended not to go higher than 300 tons because he had concerns that the frame would fail. This was a very, very stiff element. Again, lessons learned from this is that the effect of the polymer mud was overestimated, and a shorter length would actually have helped to reach geotechnical failure during the testing, which we had to perform analysis in the office using conventional methods and finite elements in order to predict the ultimate side shear. For Voorhees Avenue, 4 load test results. On the top of the page, the 2 taper piles. 1 pile failed. That was the pile that was driven to a lesser blow count of about 160 blows per foot. On the right side was the pile that was driven to 300 blows per foot. And this was actually the criterion that was adopted during construction. It was 100 feet deep or and 300 blows per foot for reaching 180 tons allowable capacity for the tapered pile. The conventional micropile just made it to 180 tons. You see on the bottom left side the test results. The best performing pile was the hollow bar. We got 200 tons and we felt that we had a little bit more to go. Then we met with the structural engineer and the owner, and we discussed how much the extra 20 tons or 30 tons will be beneficial to the project versus applying for requesting a waiver from the building department for the use of this pile. And the owner felt that waiting for 2, 3, or more months to get the waiver approved versus moving faster with the conventional micropile and having a few more was more cost effective for them. So we keep the good results for the hollow part. Again, it was really beneficial for understanding the behavior of the pile, but the project moved with the conventional micropile. And this is a comparison between the two sites, how the two conventional micropiles behaved. On the left-hand side, we have Voorhees Avenue. On the right-hand side, we have 86 Fleet. So the bond length was much deeper and was a larger pile at Voorhees Avenue, and it was a slimmer pile with only 50-foot bond length on 86 Fleet. So we got more than double the ultimate site shear in 86 Fleet, totally attributed to the geology and the density of the sand. And I consider this to be the most important slide of the presentation. Is the money shot. That's basically we are comparing the results between sites and within the same site. So between horizontally between 86 Fleet and Voorhees, we got a much higher ultimate site shear for the micropiles installed in northern Brooklyn. Again, the geology plays an important role in the density of the sand. While in Voorhees, between the different piles, we got about 16 psi ultimate capacity for the conventional micropiles, 18 for the hollow bars, and then about 11 psi for the tapered piles. And you see that the estimated capacity, our lessons learned is for the taper piles, the estimated capacity using CPT correlations was basically on the money that with the actual capacity that we got from the testing. So yes, testing saves money and time. This was the test results convinced us and our clients. For 86 Fleet, the GIEs could not have been implemented without the testing. The client was skeptical, having like sacrificial elements and then performing all this testing program. But then, based on the test results, we were able to fine-tune the length of the GIEs, the location of the GIEs, coordinate the foundation design with a structural engineer, perform analysis that basically we were able to move from a full piled foundation to just place 20 to 25 elements strategically located below the mat. For Voorhees, the testing basically showed that vibrations were not as large as initially thought. The neighborhood did not react negatively during the index pile driving. The effects on the adjacent buildings and New York City Transit were not substantial. So we were able to convince the neighborhood and New York City Transit that adapting a driven pile would not result in unacceptable vibration levels or compromise any structural integrity of the structures. So unfortunately, our clients did not want to share the exact numbers, but I can safely say that the estimated the reduction in foundation cost between the two projects was between 15 and 30%, and in both projects we saved between 2 to 3 months in schedule, considering a lot of drill piles versus driven piles. It was very beneficial for the overall schedule of the project, and both these tests did not cost more than a couple of $100,000 per site, not including the engineering. So last slide, conclusions. The local geology cannot be ignored. It's very important to understand the setting and what this means in terms of big picture geology. Designing a pile testing program is really essential, and it results in cost savings. But as I said before, it also it takes significant effort to explain the value to the clients. Trust needs to be there, relationship needs to be there. Sometimes it's very difficult to walk in a cold room and convince a client to spend $250,000 on a testing program, promising possibly savings of maybe a few million, maybe a few less, without being specific, because on consultants, we cannot be specific in the early stages of the design. There has to be, the message needs to be conveyed appropriately to the clients very early in the design process. We saw that the PDA underestimated the pile capacity in the very beginning, and the delay between installation and testing is super important for the driven piles, for the sand setup. And it's really important to select the contractor carefully. Experience and being thorough and work together with the engineer is very important in order to complete a successful project. We were really fortunate to work with a very qualified contractor on this project. And this concludes my presentation.
Okay, Tasos, thank you very much for a very interesting illustration that testing does save money. After we started in Seattle, you now see the same thing in New York. And we